Up here on the chalkboard, I have a little thing about what's happening in this problem. In this problem, it says what happens when a strontium plus 2 ion forms. And just as a quick review, an ion means that there's a charge. All right, it can be positive or negative. Strontium, a metal like most metals, makes positive charges or cations. So this particular one is a strontium plus 2. Strontium is in the same group as magnesium and calcium, so it's another positive 2. And what positive 2 means is that in this case, the strontium, which is number 38 on the periodic table, starts, if you will, as elemental strontium. So it has all of its protons and all of its electrons. So like we talked about, neutral atoms have even protons and electrons. This would have 38 protons and 38 electrons. And when I say it's neutral, it's because there is no charge. Each proton is positive 1, and each electron is negative 1. So 38 times plus 1 plus 38 times negative 1 goes to 0. The pure elements don't have a charge because they have even protons and electrons. However, things in group 2A we've seen like to be positive 2, all right? And in this context, that means that the strontium is losing 2 electrons, all right? It's gotten rid of 2 of them. So instead of 38 electrons, now it only has 36 electrons. It has 2 fewer. And if you do the same thing with positives, negatives, it's like 38 times plus 1, still has all of its protons, but now it only has 36 electrons, 36 times negative 1, so it's like 38 minus 36, positive 2. So that's what it means to be positive 2, all right? It loses electrons, all right? Like I gave away $1 in the lecture last week, which was silly, but anyway, I did. You give away the electrons, and it becomes more positive. Fewer electrons, but the same number of protons, all right? So if you go through these questions, first of all, to become positive 2, it's not going to lose 1 electron, it's not going to lose 3 electrons, it has to lose 2 electrons. Now it says the same number of electrons of either xenon or krypton, all right, well, the strontium plus 2 has 36 electrons, so if you go to the periodic table, number 36 right there is krypton. So for this one, it would be answer D. But I think this is kind of a nice description because it shows like why they're positive or why they're negative. Remember, protons don't change in the elements. If you change the number of protons, it won't be that same element. So you take away a proton from strontium, it would become rubidium. You add a proton, it becomes yttrium, stuff like that. That will change the element itself. So you're not doing that, but we will play with the electrons a lot. And the metals tend to lose their electrons. Non-metals tend to gain the electrons the metals lose. Any questions on that? Okay. So here's a question with 5 different combinations of a name with a formula. And one of these combinations is incorrect. And see if you can figure out which of these 5 is the incorrect formula with name combination. All 5 of the, except for the middle one, excuse me, the other 4 do have polyatomic ions, so just realize that's like phosphate, hypochlorite, nitrate, sulfate, ammonium. take a guess which one of these up here is an incorrect combination.
D.
Bam! Well done, D. Here's why D is funky. Polyatomic ions, like the main group metals and the nonmetals, have fixed charges. And ammonium is +1, and phosphate is -3. So if you're going to make a combination between ammonium and phosphate, then you need 3 +1 ammoniums to balance out the -3 phosphate. So ammonium phosphate would be NH4 in parentheses 3 PO4. These other ones are okay. Calcium +2, sulfate -2. So the positives and negatives cancel. Nitrate or sodium +1, nitrate -1. So +1, -1. That's legit. Magnesium, we saw +2. Each iodide is -1. So 2 -1s for the +2. Cool. And hypochlorite is ClO -1. Well, calcium's +2, so you need 2 -1s to balance the +2. This is just one of those questions. The more familiar you are with the polyatomics and this naming, it gets easier and easier, okay? Any questions on that? Here's another question that's related to the bonding. One of those up there does not involve ionic bonding, all right? What's the name of the other bonding that happens a lot in chemistry? Covalent. Well done. So this other one up there is a covalently bonded molecule. See if you can figure out which one it is. And the one that isn't ionic has a different set of atoms to it than the other ones too. Ionic bonds usually have something positive and something negative, all right? And the negative parts are chloride, oxide, fluoride, nitrate, carbonate. They can be polyatomic ions like these guys. They can also be individual pieces. But if it's an ionic compound, then the negative part will have a positive piece with it. And the positive piece with it is usually a metal, sometimes polyatomic like the ammonium. So like lithium is a metal, aluminum, barium, those are metals. Sodium is a metal, definitely. Hydrogen can be metallic, absolutely. But is sulfur a metal? No, right on. This metalloid line is, again, pretty important in what we're talking about. And sulfur, number 16, is above that metalloid line. It's up and to the right. So sulfur is not a metal, all right? And when you have a nonmetal and a nonmetal come together, they tend to share their electrons, the covalent bonding. So sulfur dioxide is not an ionic bond. That's going to be a covalent bond, all right? The nonmetals and nonmetals together, when they come together, it's a different kind of bonding. The sharing of electrons is the covalent. The ionic bonds are usually metals and nonmetals, or some kind of polyatomic ions, that kind of stuff. It's the nonmetals and nonmetals that are the covalent ones. Questions on that? Cool. All right. Oxalate is a polyatomic ion, and it's one that you may or may not know about. Sodium oxalate has this formula right here, and I'd like you to use this formula to figure out what the formula for iron 3 oxalate is. So if you know what oxalate is, you can go ahead and put it in right here and figure out how the iron and the oxalate come together. But if you don't know oxalate, because this is a little bit weird, don't worry about it, you can find the charge of the oxalates from the sodiums. So see if you can figure out without Googling it, although if you really want to, you can. See if you can figure out what the formula for iron 3 oxalate is. You're seeing the difference here between a main group metal and a variable charge metal, all right? Sodium oxalate, it involves the main group metal sodium. What's the charge on a sodium ion in these kind of compounds? +1, well done. All the group 1As, sodium, potassium, lithium, etc., they're all +1. So sodium is +1, and there's 2 of them. So that's a total of +2. And the oxalate, the C2O4 thing, gives enough negative charge to balance that +2. So what must the charge be on an oxalate ion? -2. Outstanding. So this is one way you can find out the charge of these weird polyatomics. There's literally thousands of these crazy polyatomic ions, but if you have something like sodium oxalate, you can figure it out. So one day in the future, you make a new compound, and it's sodium blah, 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 and I have no idea what blah, blah, blah is. It's okay. If I know there's only one sodium, then I know that blah, blah, blah has a -1 charge, all right? And that's kind of powerful when you don't know a lot about biochemistry, for example. But anyway, prop that back on. So this is one way to figure out these countercharges of things, all right? Sodium is going to help you out. So, crazy oxalate, -2. Iron here, +3. That's what the iron Roman numeral 3 means, all right? If it was iron 2, it would be +2, etc., etc. So when these two come together, you've got to make sure that the positives and negatives cancel. So 3 times 2 gives you common denominator of 6. 6 divided by 3, you would need 2 ions. 6 divided by 2, you would need 3 oxalates. So the formula Fe2C2O3. Now, I hate using crossover because it doesn't work all the time, but it is a powerful tool, especially if you get stuck. So put the 3 by the oxalate, put the 2 by the iron, and like we talked about, more often than not, that will work as well. So by hook or by crook, the formula here, Fe2 parentheses C2O4 parentheses 3. And again, sometimes it's cool because those fixed charge metals will help you figure out the charges on things if you don't know for sure what it's going to be. Any questions on that? Here's some compound statements about ionic compounds. And I think instead of us going through and answering it, I'm just going to go through and talk about them one by one. So the first one, so remember that ionic compounds are when the positives and negatives come together. And the first one says, as the ionic charges increase, the attraction between the ions increases. And this part is true, all right? If you have a +1, -1, that's like a single handshake. Hey, Wes, haven't seen you since last Wednesday. On the other hand, I haven't seen Wes in a lot longer. I say, Wes, so good to see you. And I do the double handshake thing with them and stuff like that. All right, other people go, come on, break it up. It's harder to break up a double handshake than it would be a single handshake. On the other hand, if I had a third arm and he did too, I could say, Wes! And I'd bear hug him or whatever you do with 3 hands, I don't know. But it would be a tighter interaction, all right? And this dumb example is what this problem's all about. Number of charges goes up, it makes for a stronger bond. So positive 1, negative 1 strong, positive 2, negative 2 even stronger, positive 3, negative 3 would be stronger yet. So the first one, definitely. Second one, ionic compounds form extended three-dimensional networks called crystal lattices is true. I showed you some pictures how it goes like sodium chloride isn't just one Na and one Cl, it's NaCl, NaCl, NaCl. And it's in all dimensions, all directions, all right? So instead of having just one NaCl to break up, it's actually a lattice of sodiums and chlorides to break up to make it happen. And they're very, very strong. So the next one is true as well. C is also true. I showed some pictures of, I think it was a potassium bromide crystal, and it literally was like nice and sharp. Crystals, as you probably know, are usually very sharp and shiny sometimes even. That's because these bonds are so strong, and you can cleave it along like a particular axis and still have most of it being together. D, the fancy name for positives and negatives, is not handshakes, so I apologize for that. Fancy name is electrostatic forces. Electrostatics are the fancy name for having positive, negative forces, sometimes called Coulombic forces as well. And then the last one, though, calcium oxide, that's going to be a positive 2, negative 2. Remember, calcium's always positive 2, oxygen in group 6, negative 2. So that's like a positive 2, negative 2 handshake. Sodium chloride would be a positive 1, negative 1 handshake. So this last one is the one that's not correct. And it's not correct officially because of Coulomb's law, which is this thing right here. In chemistry, we say that the force depends on the number of positives and negatives. That's positive 1, negative 1 versus positive 2, negative 2. Positive 2, negative 2 would be stronger than positive 1, negative 1. The other thing is it does make a difference, the distance between the ions. So if you're close to each other, you can shake, but as you start walking away from each other, it gets harder to hold on until finally you've just got a hand, like a pinky, and then you finally break it up. So that's what this thing tells you. As distance goes up, the forces go down, not as strong. The more, though, positives and negatives talking to each other, the stronger it is. Any questions on that? Sweet. Now, here's a question. It says we have 0.25 moles of each of these elements. And the question is, which one has the largest mass? Which one has the most grams? So we're starting with moles. We want to go to grams. We're going to need the molar mass. You can calculate these actual numbers if you want, or going from moles to grams means you're going to multiply by the molar mass on the periodic table. So maybe instead of figuring out what each one of them are, maybe you could find the largest molar mass. Think about that one for a second. let's look at the last two real fast, calcium and carbon. All right. There's two different ways to do this problem. I gave you a hint to the shorter way, but you could go through and find the grams per mole of each one of these. So as an example, calcium is about 40 grams per mole. You can do better sig figs, but on this kind of problem, don't worry about it. And carbon is about 12, all right? Well, this is like 1/4. So 1/4 of 12 would be about 3 grams. The moles would cancel out. And again, this number just comes from the periodic table value for carbon. On the other hand, 1/4 of 40 would mean about 10 grams of calcium. So you can tell that there's going to be more calcium mass than there would be grams of carbon if the moles are the same. But more importantly, this number was bigger and that created more mass, all right? And this number was smaller and it created less mass. So one way you could do this problem is just look for the element here with the largest molar mass, with the largest value like this. Do any of these elements have a larger molar mass than calcium? Yeah, which one of those has the biggest molar mass? Zinc. Well done. So here's the actual molar masses of the different elements from the periodic table. And again, you can ignore both of those things on the right. Just look at these columns. Zinc has the largest molar mass. The periodic table, always open to you. And more often than not, as you go left to right on the periodic table, the molar masses get bigger. It's not 100%, but it's pretty close. So the biggest one, the last one on that list then there is zinc. Iron is close to it, but not quite as big. That would be another way to solve this problem. You just want the largest molar mass. Largest molar mass creates the most mass. You can say there'd be 16 grams of zinc. So again, you could go through, solve the mass each one of them, and just circle the one that's largest, and that's fine. However, if you also just look at the largest molar mass, that would be a good way to do this one too. It's up to you. People have different choices. Questions on that? Now, this is kind of a question that sometimes is kind of interesting to think about, all right? And this question says, calculate the average mass of one chromium atom, all right? Well, first of all, what's the symbol for chromium on the periodic table? CR. CR, well done. CR is number 24, and notice there that number, 51.9961. So if I wrote 51.9961, and I wanted to think about it in terms of molar mass, what would be the units for this 51.996 number? Grams per mole. So this would be grams of chromium in a mole of chromium. Now remember, another unit that you've got to know around this class is good old Avogadro's. 6.022 times 10 to the 23rd atoms per mole. And in this question, what you want to do is you want to find the average mass, grams per atom. So notice here, you've got moles, you've got moles, you want grams per atom. See if you can do this. I'll give you a minute or so. If you can do it, cool. If you don't feel like doing it, that's fine too. Answer E is not correct. I know. That makes you wish it was. Darn these chemists. I'm just the messenger. No, anyway. This is a fun problem to amaze your friends and family. Just joking. So on a question like this, all right, first of all, dimensional analysis can help you out because the 51 number is grams per mole. Avogadro's number, in this case, would be atoms per mole. So you can see what I did up here. I essentially flipped this upside down, so it was 1 mole per Avogadro's number. And you can do that with all these conversion units. So the moles cancel out. The units will be grams per atom, okay? And the only thing tricky here is that you're dividing here by one of these powers of 10. And if you're not careful with your powers of 10, it'll look like 51.9961 divided by 6.022, but then on top, it'll try and multiply by 10 to the 23rd. So if you get a really big number here, it's because the calculator doesn't realize you want the 10 to the 23rd to go with the 6.022. So again, I wrote intentionally the E button right there. That EE button on your calculator can be so helpful. You could also put the whole part in the bottom here in parentheses. That would be another way to kick it. But either way, 51.996 divided by Avogadro's will be the answer, and this is the mass per chromium atom. And it comes out to be 8.634 times 10 to the minus 23 grams. So if you had 1 atom of chromium, which you couldn't see, and it wouldn't fit on my finger, it would go through my finger probably, but anyway, very, very small amount of mass. And that's kind of cool. So you can't have a mass of chromium less than this number. Like you couldn't have 5.6 times 10 to the minus 23 grams of chromium. This is like the smallest division of mass, which is kind of an interesting thought philosophically, but anyway, if you see anything about mass of an average atom, it's what you do. Molar mass of the element divided by Avogadro's. Cool. Questions? Here's a question that says, what answer best represents the percent composition of carbon dioxide? And this is something we just talked about today, so I kind of want to help out here a little bit and figure this out. So if you had a sample of carbon dioxide and someone wanted to know what it was, the first step you would do is you would get an elemental analysis for it. And there's some techniques to do this. All right, I used to use something called atomic absorption, but there's other versions of this out there right now. If you have the formula, though, and this is what we talked about today, if you wanted to find percent carbon, you would have the molar mass of the whole thing on the bottom, and on the top, you would have just the grams of what you're looking at. So as an example for carbon, you would have 1 carbon, or 12 grams roughly on the top. We do need the molar mass here of CO2. What's the approximate molar mass of an oxygen atom? 16, good. You're starting to see, some of these are going to pop up. Carbon, hydrogen, oxygen, sometimes nitrogen. They're going to be used a lot, so that's cool that some of you are starting to see it. So yeah, oxygen, about 16. Approximately, what is carbon? 12, right on. So 16 times 2, 32, plus about 12, about 44 grams per mole. That's the molar mass of CO2. So the percent carbon would have 44 on the bottom, and on the top, you would have 12 grams. You have 1 carbon, so 12 grams divided by 44 will give you a percentage. For oxygen, you would have 2 times 16 on the top, but you would also divide by 44, the same molar mass value, all right? And at this point, then you can plug and chug into your calculators. So in these values, I ended up with 27.3% carbon and 72.7% oxygen. If you look at these numbers a little closer, 44.01 is the molar mass of CO2, just to a few more sig figs. There's 1 carbon, so 12.01 top divided by 44. The oxygen, here's the 2 times 16 part, so that divided by 41 gives you that. And again, to check yourself, the percentages of both of them together should be pretty close to 100%. You could have also gone 100% minus the percent carbon to find percent oxygen. That would have been legit as well. Any questions on that process? Cool. So just remember, if you see anything about finding a percent of an element in that compound, molar mass first, and it goes on the bottom, and then the grams of the element go on top. Cool. Now, here's another kind of problem. Here we have a nitric oxide compound, NXOY. And there's a whole bunch of these. Today we saw NO, we saw NO2, we saw N2O4. There's also N2O, N2O3. There's a whole bunch of these. But anyway, this particular one, 46.67% nitrogen. All right? Now, if there's only nitrogen and oxygen, how do we find percent oxygen from this data? Subtract it from 100. Well done. So 100 minus 46.67. That would be the percent oxygen. Now, what we're after here is the empirical formula, smallest whole number ratio. And remember that if you see a formula like this, it's always a formula based on moles. So what I would do on this problem to solve it, I would take the percentages and turn them into grams. Assume 100 grams total. So this would be 46.67 grams of nitrogen. I would then take the grams of N and the corresponding grams of O, turn them into moles. Bigger on top, smaller on the bottom, you'll get a ratio. If it happens to be 2 to 1, for example, it would be NO2. If you get a 2.5 to 1, you might need to multiply by some factor like we talked about. Do you want to, see if you can work on this problem, or if you don't want to, just wait a second and then we'll talk about what the answer actually is. problem like this. Turn your percentages into grams. All right, I would assume just 100 grams. So that means you'd have 46.67 grams of nitrogen, and 100 minus 46.67 means that you have a percent oxygen, the other component here, 53.33% oxygen, and that would be 53.33 grams of oxygen. Formulas like this are based on moles. So the next thing you want to do is just turn the grams into moles. So 46.67% became 46.67 grams of nitrogen. On the periodic table, nitrogen's about 14.01 grams per mole. So I had 3.331 moles of nitrogen. And down here, the 53.33% became 53.33 grams of oxygen, divided by the molar mass of oxygen from the periodic table, 16-ish grams per mole, 3.333 moles of oxygen. So initially, this is a rough formula, N 3.331, O 3.333. Officially, divide both of those numbers by the smaller one, so 3.331 is smaller than 3.333. But you can tell that it's basically like 1 to 1. So the empirical formula here is just going to be NO. It's basically just 1 nitrogen to 1 oxygen. A little bit of percent error, like we talked about earlier and stuff, but boy, pretty close to 1 to 1. So percentages to grams to moles, compare them, empirical formula, whole numbers, no fractions. Cool. Questions on that? Okay. I'm not going to spend a lot of time on this problem. This is like the tin iodide problem we did. And in this problem, all of the zinc reacted, but not all of, but some used some oxygen. Notice how the mass increased upon going from the pure zinc to the compound. So the difference between those two would be the grams of oxygen in this case. And if you have a formula, you're going to need moles of zinc and moles of oxygen. You can turn this number into moles of zinc, and the difference between those would be grams of oxygen, which you can turn into moles to find the ratio. And again, long story short, 6.54, all of the zinc was used up, so I turned that into moles. The difference before or after versus before, 1.60 grams, that's the oxygen that was added. So I turned that into moles, 1-to-1 ratio, zinc oxide. All right. But I'm more interested in doing the next problems, I'll be honest, so I'm going to kind of skip this. Any questions? Now, this is the question, though, I think is worth talking about. Glyceraldehyde has an empirical formula of CH2O. The molar mass of whole glyceraldehyde molecule, 90.08. So this is the kind of question where we have an empirical formula and we want to turn it into a molecular formula. And to do that, you do need a second piece of data, which is the molar mass of the compound, 90.08. This problem might look familiar to you from before, because I'm using some of these, sorry about that. But anyway, you'll need to find the molar mass of the empirical formula, the CH2O, and compare it to the molar mass of the whole thing. So see if you can find out which one of those is a reasonable expression for the molecular formula of this glyceraldehyde. So for CH2O, we know that's the empirical formula. And one of the things I would do right away is find the molar mass of the empirical formula. And you can use really rough sig figs. And so notice here I'm using just simple ones, the numbers we've talked about so far. So like carbon would be 12, and there's 1 of them. And hydrogen is just 1, and there's 2 of them. And oxygen, 16. So it's about 30 grams per mole, all right? That's the molar mass of just the empirical formula. And the reason I can get by with using cheesy sig figs is that the ratio of the molar mass of the whole thing, that's the 90.08 number, to the empirical formula's mass is always going to be a whole number, all right? There won't be fractions or anything like that. So roughly, what is 90 divided by 30? 3, that's right. This ratio is what goes right here when you're finding the molecular formula. The molecular formula will always be the empirical formula raised to a number. And what we just found there is that we want 3. So we'd say CH2O to the 3rd, or better yet, multiply all of them through by 3. So you'd have 3 carbons, 6 hydrogens, and 3 oxygens. That's why on this part right here, you can use very rough sig figs. I know we made a big deal and problems that one about sig figs, and they are important, but in this part right here, you can get by and save yourself some time by just using kind of whole numbers. Questions? Now, this problem is kind of the whole shebang, all right? It's putting it all together. And I think I'm going to leave on this problem, but I'd like you to think about how this, start working on it. This one, we start with percentages. We also have the molar mass of the entire compound. And to get to the molecular formula, this is kind of the holy grail of this material. All right, finding this is pretty cool. So see if you can do this. I'm going to start putting some notes on the board, so if you get stuck, you can kind of look over here and then start to get unstuck. If you can do this problem, you've got this stuff down. any of you need to buzz, it's totally legit. Answer. I apologize, I'm running out of time, so I kind of need to get this going. Up here are the steps that I use to solve it. And 100 grams total, so 75.41% fluorine would be 75.41 grams of fluorine. And then the rest of it's phosphorus, so 100 minus that number would give you the grams of phosphorus. I turned them into the moles of fluorine and phosphorus. This is a rough formula. Divide both of those numbers by the smaller moles, which in this case was 0.794 moles. So that came out to be PF5, 1 phosphorus for every 5 fluorines. That's the empirical formula. Now, phosphorus is about 31, and there's 1 of them. Fluorine is about 19, and there's 5 of them. So that's about 126 grams per mole. That's the molar mass of the empirical formula. So you take the whole thing, 251.94, and divide it by that, you should get a ratio of 2. And this ratio will always be whole numbers. So that means you need 2 PF5s, P2F10 would be then the fancy formula. And that's what all of this stuff is right there. Questions on that? All right. There's only 2 more questions. Iodous acid would be C. It's HiO2. And this just lists all the different acids and stuff you might have. Yeah, if you have a phone you want to take a picture, that's legit and stuff. So. And the last one is a hydrate. So nickel 2 hydrate, hexahydrate. Nickel 2 nitrate would be NiNO32. Hexa is 6. Hydrate means 6 waters at the end of it. That's the only other thing. And you can find the molar mass from there. Sweet. Done. All right. We're going to do problem set 3 on Wednesday. That'll go over more of some of these last problems and stuff. Have a wonderful day. I will see you all on Wednesday. Thanks for sticking around today.